So I have all this late 80s, early 90s memory modules, 30 pin, 72 pin, 168 pin, buffered modules, single inline module and dual inline module. And I'd like to actually categorize, document the size, and test the integrity of these modules. I have a whole box of these, and of course there's plenty more in the machines that I use them with. So sometimes these have printed stickers which indicate the size and specifications of the memory modules, but oftentimes they don't. And that's a little bit more difficult when we need to look up the packaged specifications and figure out what the module is based on what package is actually installed on the module. Thankfully, at one point in time, I was able to pick up one of these SIMMCheck modules from Innoventions. And normally these are pretty expensive by my standards, but a few years ago, I was able to get this early model SIMMCheck II with a 168 pin module installed on it. It was about $125, but didn't have a power supply. I presume this works. It's a little bit used, but it seems to be in otherwise good physical condition. So let's get some power to it and see if we can use this to test some of these modules. You can see on the bottom here, we have a positive center on a barrel jack, and it requires 9 volts between 2.3 and 3.3 amps, which shouldn't be too hard to do. I have a bench power supply that I can dial into up to 30 volts and 5 amps. So let me set that to the required specification and run a wire over here to see if we can test some of these memory modules. Power this light on just for fun as well. So the first thing I'll do is just plug in a light bulb to this power supply and use that to dial in the current and voltage specifications so that it gives the correct power for this SIMMCheck unit here. This light bulb is a dual filament high beam low beam from a vehicle, and half of it's burned out, so only one filament still works, but that's perfectly usable for this case. I'm just going to attach the 2 leads to the 2 pins on the good filament here, the distant ones in this case, and I'll start by just turning the voltage up while the current is set as low as possible. We'll start turning the current up. And it is taking the current. Up to about 1 volt here, and we do start to see a glow in the light bulb. And as the current comes up, the voltage grows as well. Once that exceeds 9 volts, we'll actually turn the voltage down to cut it. It's up to 9.5. We'll cut that voltage down. To 9.0 here. And we're at 4.3 amps, which is well in excess of what this SIMMCheck needs. So we can leave this here at this point, and we'll know that that SIMMCheck will be able to draw a clean 9 volts up to at least in excess of its 3.3 amp specification. In the interim, we'll make sure these stay separate and give a extension lead to make sure that we can get all the way over to this SIMMCheck unit. I'm just going to use some speaker wire here. It should be a large enough gauge to provide a high amperage without too much voltage drop. And this has a stripe on the edge of one of the contacts, I believe. Well, if it was a higher quality product, it would. This is actually identical on both counts, so we'll have to use a multimeter to figure out which side is positive on the other side of the wire. Either way, this is long enough and high enough gauge that I'm not worried about the actual transmission of current. I have this multi-port adapter, which was used for another project. The cut end I've just separated so that it doesn't make any contact. And this end here actually has been modified with these two little terminal points. I'm going to use these and then use electrical tape just to make sure they can't make contact with each other. Power supply is still separate over here. Haven't plugged that in yet. But I'm going to connect these two into these little open terminal ends and then just put some tape on it to make sure that we are making good contact and aren't allowing these 2 points to bridge and contact each other. All right, these 2 points are making good contact. Let's just apply some electrical tape here. Okay, I have the first terminal completely taped off and plenty of slack here on the cable, so I actually tend to just wrap the second one in at this point, ensuring that they don't contact each other, but keeps it nice and compact when we do 2 connections in one piece of tape here. Just like so. Now at this point I have this guy here connected to my cable. I am going to grab a multimeter. I'll set this for 10 volts DC. And just use the 2 contact points here. I'll leave that in there for center as positive. Pull this rubber over the front of those connectors so that they don't make contact with each other. Let's see if we have this right the first time. And we do. So that's a center positive 9-volt connection from that power supply behind me. And when we plug this into the SIMMCheck, we should have good, reliable power up to 3.3 amps or higher. Okay, we're plugged in. Let's try turning this on here. Looks like we're good. There's no modules inserted, obviously, so it won't actually pass, but if we do F1 to start basic test, I assume we'll get no memory, as we expect. Someone here posted this message here. When testing 72 or 30 pins, remove the DIMMCheck 168 adapter. We'll just demonstrate what that looks like here. This is just a module that sits on top of this adapter slot. And on the bottom here, just provides, I imagine there's more than just this particular module adapter available for this unit. But when not testing a 72 pin, gives us the option to plug in a 168 pin adapter. Since we do have a 72 pin SIM here, let's just plug this in and give it an initial test. These just bend this way. Push those away and insert that adapter like so. Let's just see what happens here. And we're testing. It's a 4 megabyte module. We'll perform an extensive test. Okay, so 4 megabytes, it's like 16 nanoseconds. We will escape to exit and remove this module. And it looks like this actual SIM here, the packages on it are rated 70 nanoseconds. what this tester is testing it at 60 nanoseconds, potentially detected or potentially just assumed. Not sure yet. Either way, we will label this module. We'll label this as it tests. Four megabyte module, 5 volts, FPM. Next thing I'll do is just test the 168 pin adapter that this came with. Reinsert this here. It looks like maybe this had 2 clips at one point, but this one is missing. Shouldn't matter as long as the pins actually hold it well enough here. Wait for that to start up. I do see DIMMCheck 168 on the screen there. This module looks like it is labeled potentially a 32 megabyte module, and this is not a DDR module, it's buffered, and we'll see what this reads. Just let that sit like so, and we get a size measurement error. Let's just make sure that this is seated well. Wiggle it back and forth just a little to see if the contact improves. And so far so good. This seems like maybe a 50 nanosecond FPM. 32 megabytes as that sticker indicated it would be. Here's the buffer specification. We'll let it do the extensive test as well here. Okay, it's a good 32 megabyte module. This one tested out at presumably 15 nanoseconds, but again, this is a 60 nanosecond package rating on at least most of these visible packages. That's just fine. I'll label this one now. That'll do. There's another 168 pin module. This one has double the number of packages on it, but let's see what the actual density is. It does seem like it draws a little bit more power with all those packages on the module. 55 nanosecond test at 5 volts. 8 by 64 is a 64 megabyte package. Did it do an extensive test? Okay, we're passing 64 megabyte module. And let's label this one. "55 nanosecond package test." Looks like these are rated 60 on average. So the rating tends to be just a little bit conservative compared to what the tester assumes the modules are, which is perfectly expected. We'll do another 168 pin here. Let's see. Give that another couple tries to connect. we go. 53 nanosecond is what it says here. Like another 64 megabyte module, 5-volt FPM. Another good module. Looks like 55 nanoseconds was the final test. And label this one here. Next unit here. Looks like a smaller module. Probably not nearly as dense, but we'll give that a try. Need a little deoxide on those contacts, but second try seems to work. Initially 67 nanoseconds. Might be a 70 nanosecond package rating. Have to look afterwards here. Let that run the extensive test. Give that a second try here. Seems like some of these pins just might not be as clean as they need to be. Bounce that up and down just a little bit. Most of the pins look pretty clean. Data bits. Maybe it's just contacts. We'll give that a second try. We'll see if it passes the extended test at this point. Looks like an 8 megabyte module. It's at least beginning the extended test this time. Okay, and we do pass. Maybe just a little bit dirty on the contacts, but that's enough for me to label it. We'll know that the actual packages seem to be in good operable condition. We did end up with a 70 nanosecond test, and it does look like these are rated for 70 nanoseconds on the package in the silkscreen, so not much margin there, but it is accurate to what the test has concluded. Yeah. We do have one more 72 pin here. This one seems maybe not quite as dense as the other ones we had tested, but certainly more dense than the ones we just had. Give that one another try. That's actually moved locations here, which bits are not testing good. Back to the first one. Same. Give it just a few more tries here, but that might be a legitimate failure. Yeah, this bit here where it says F maybe disconnected, inoperable, or just permanently failed. Just a couple more tries, but I think this might just be a legitimate failure of the module, since it's so consistently returning that one failure. Yeah. So that one will stick with it. I'll print that out and maybe we'll repair that at a later point. Looks like within that failed range here, only 6 of the 8 bits are actually returning null values. And that's consistent. 40 through 45, those are the ones that are problematic there. Let's give it a tag which reflects something like the tester found. Indicating that that specific set of bits contains failures. It's not quite as descriptive as the readout here describes, but good enough to know that there's a failure, but it's pretty consistent and isolated failure, and that's something that I might consider looking into and repairing at some point, because these 128 megabyte 168 pin buffered DIMMs are actually pretty valuable. They're kind of the top spec that you can have in this form factor. So if I could repair this, it would be worthwhile. And the last thing I'll do is 30-pin sim. Now this SIMMCheck doesn't actually have a slot for a 30-pin sim, though it does allude to a 30-pin sim being one of the options to test with. What I can do is use something off the shelf like a 30-pin to 72-pin readapter, so that you can, this was originally designed so that you can take 4 of your 8-bit sims and install them into a 32-bit 72-pin sim slot, reusing the investment that you had presumably paid for an earlier system on your newer system. And this will probably test correctly in the 72-pin slot of this tester. So let's give that a try as well. Start that up again. Let's say sim here. Let's see what these are and if they're inserted well and if they're making good contact. Like 65 nanosecond, 1 meg by 36, 4 megabyte. Let's give that a longer test as well here. Okay, so we have 4 megabytes. These are each, looks like 9-bit. Parity check on them. But each of those 4 are good. Each are rated 70 nanoseconds. Looks like, at least on the bottom module there. But even though we can't individually test 30-pin sims, we can determine that each of these 4 are good using this SIMStack adapter here. So we'll go ahead and label each of these four. Quite sure if FPM is the correct term for this 30-pin memory. Could be just detected that way when it's aggregated to a 72-pin module format, but not knowing better right now, that's what I'm going to put on these stickers. When trying to test another set here, let's just try to find others that are like it. Thankfully I have a bag here, but if I can get four of what look like roughly the same module, I'll have a pretty good chance of being able to assume these are correct. Looks like I did label these 4 megabyte at one point, which I presume means they also work. It looks like a complete set of 4 there. Load these into the same adapter and just verify. I mean, this should be a 16 megabyte set. Thankful that this multi-SIM adapter here uses metal spring contacts, because the plastic ones do not last very long, and since I intend to use this as a testing median, it's nice to know that I'll be able to reinsert new modules into this without worrying. Okay, there's 4 of these presumably 4 megabyte good modules. Let's just give this guy a test now. Let's see. Oh, this one does not look fully seated. That will help. Better. Like a little over 70 nanoseconds. 16 megabytes. I'll let it perform the extensive test there. Okay, we're good. 73 nanoseconds is what it expects this to be. Let's look at what some of those ratings were on the chips there. And they're rated 80 nanoseconds, so again, a little bit faster than what's advertised, which is just fine. Print some labels for these guys. Nice to be using the label maker that I had repaired in a video a few days ago. This is perfect for this operation. I'm just being able to print directly off the computer for all of these modules that I'm testing, and just makes it easier to find them later. If you haven't checked out the video where I repaired this, there was a spring inside that had just broken off, which had prevented the roller from making contact with the tape, and so it wasn't feeding. Check that video out if you're interested in repairing one of these. I'll just do one last set of 4 that I have sitting right here, and we'll see what these are. Load these in a similar way. So try here. 60 nanoseconds. Looks like 4 megabytes, or 1 megabyte modules. Let that run the extensive test. Okay, and those passed. close some labels here. That's going to do it for right now. I have so much more memory to test, but that's a quick demonstration of how this tester works, and it seems pretty reliable for testing 168, 72, 30-pin memory slots. There are later models of this, specifically the DIMMCheck. This is a SIMMCheck II, but the DIMMCheck is a more modern unit that actually has adapters available to run DDR, DDR2, DDR3, but substantially more expensive. And this honestly is not found very cheaply either generally. These are far less common because they were early units, but this model I acquired more cheaply than I would pay for generally what these are available. So I probably won't end up with a newer unit, but it is very nice to have the ability to test 168, 72, and 30-pin SIMs of the early generations, and I will be using this a lot to make sure that the modules that I have in my existing systems are reliable and that my stash of available memory is also tested ahead of time, so I don't have to guess when I install modules whether they're good or whether the symptoms I'm experiencing in a machine are related to that memory or not. There can still be, as we saw, discrepancies in the actual contact that memory makes in the SIM and DIMM slots, but knowing that the memory is fundamentally sound is a pretty good service to understand what diagnostic point I'm starting to work with when I do encounter errors. So this is a great unit and I'll continue to use it. I will probably get a proper power supply. The power supply is running over there, which is just perfectly fine. Reading the amperage readouts, it does look like it can peak close to 3 amps on 9 volts. So certainly 2.3, 3.3 is what it asks for, and it will use most of that allotment. So don't skimp out on the 9-volt supply on this unit if you have one. Anyway, that's going to do it for right now. We'll probably continue testing, maybe more on camera, maybe not.